Modern farms and agricultural operations are vastly different from those of a few decades ago, owing to technological developments such as sensors, devices, robot, machines, and information technology. Today's agriculture routinely uses a lot of technologies that can help farmer in the field. These advanced devices and precision agriculture system allow businesses to be more profitable, efficient, safer, and more environmentally friendly. Here, we representing to all, a device called Maize Meter, colorimetric analysis of anthocyanins in blue maize. My name is Alia Aswa and in supervised under TS Dr. Nur Fatiha Binti Azmi, TS Dr. Faiz bin Arith, and Dr. Hazwani Binti Mokhtar. Blue purplish maize is a regular yellow corn with high level of anthocyanins which gives it a blue-purplish hue. Because of its striking color, the grain has gained popularity recently due to its health benefits derived from anthocyanin, which contains antioxidants. As we know, maize become bluish because of the anthocyanins value. In assessing whether the corn is ready to be harvested or not, the correct and accurate way to visualize the blue-purplish anthocyanins in a blue maize among the small-scale producers is important. However, the problem is how can we determine the ripeness based on the color? And can we quantify the color? So that everybody knows the standard value of blue maize. This diagram is from Digital Agriculture for Small-Scale Producers, Challenges and Opportunities. As we know, any smallholder farmers are producing for a small-scale market. So, to help farmers or a small-scale producers bridge a pending food gaps, digitalizing the operations by employing IoT and in-situ sensor can help them to produce and sell more into markets. So, this study is aimed to contribute to fill above-mentioned gap. Therefore, this project's objectives are to design a low-cost colorimeter to measure the anthocyanin color values in a blue maize, and the second one is to analyze the anthocyanin color values of blue maize via an IoT implementation. This is the flow of this project. First, is circuit diagram show the electronic component. Next, AutoCAD software for 3D design. Then, the calibration process was done by measuring the color checker by X-Rite where we calculate the color error from the device. Once we get the perfect calibration, we can start the device. Device must connect the internet to operate. After that, color value of maize has been measured, recorded, and collect all data for the maize color value. Finally, the application shows the indicate about the RGB color and also the condition or maize it is in mature or immature. Next is the list of components used in Maize Meter. We employed color sensor for measured and detected the RGB color value, battery 7.4 volt for supply, Node MCU for microcontroller, OLED for display the RGB color value and maturity, charging module to make it chargeable, buzzer, switch on off, and push button. This is the working principle. First, switch on the Maize Meter, open Blink application if necessary, connect the device with the internet, point the device's tip to blue maize. Then, push and hold until buzzer sounded 2 times, and lastly, the data of the RGB will display in the OLED and application. For color accuracy, the color meter with different tip have been tested for 3 times on the color checker. The collected measurement is first, no tip. Second, DIY tip, and lastly, 3D printing tip. The data has been collected to analyze and observe the color error based on the result of RGB value. Color error has been calculating by using Euclidean distance formula. According to the graph, measurement with 3D printing tip is nearly to 0 color error. That's mean value of the color is almost correct with real color. As the result, the average for 3 measurements has been calculated. For average value without tips is 122.99, DIY tip is 36.39, and lastly, 3D printing design have lower average number it is 32.43. So, 3D printing design has been choosing for our Maize Meter. Then, this table shows the database for immature blue maize that been recorded and tested for 3 times. In table also show the RGB value and LAB value of the blue maize. This part to analyze the color of maize when it in immature condition. For LAB result, Wolfram Mathematica has been used to analyze the LAB value. LAB color space value was analyzed because it resembles most on how our eyes see color. Next, this table shows the mature blue maize that been recorded and tested for 3 times. In table also show the RGB value and LAB value of blue maize. This part to analyze the color of maize when it in mature condition. After the database was created, the maximum and minimum RGB values were calculated. The range for mature and immature blue maize can be determined and used to finish the coding based on the data that we have collected. After the data for mature and immature maize recorded, the EOT part can be implemented. The color sensor detect the color and sent the value of RGB to the Node MCU. The Node MCU will send to the application Blink. The device also needs to connect with Wi-Fi. So, the device will sync to application. The Blink dashboard in the right side. It shows the RGB value and also the condition of maturity of maize. This application is useful for a real-time monitoring for determine the ripeness blue maize. We can send the condition to the owner in a real time. For this part, we did a measurement under different lighting condition, under the sunlight and secondly, in the photo booth to validate our device. The table show the result for RGB and LAB color value for 3 times of different maize. This is showing the result for measurement in sunlight. Maize meter shows the maize in already mature and ready to harvest. According to recorded database, the color value for direct sunlight in the morning is almost same with the value in lab. To test the validity of the measurement, the same maize has been measured and all of them is matured same as the measurement with direct sunlight. The result for measurement in lab. A farmer's user satisfaction survey has been gathered. We have asked 6 farmers that plant a blue maize in Malaysia to comment and demonstrate their interest. After being explained, shown a video, and using the device, 5 of 6 farmers express interest, while 1 does not. We concluded from their comments that it is only helpful to small-scale farmers. And that is our goal: to assist small-scale farmers. As a conclusion, we have achieved our objective, which is to design a low-cost colorimeter to measure the anthocyanin color values of blue maize in RGB color space. Secondly, is to analyze the anthocyanin color values in blue maize via an EOT implementation. At the end, we can have a database for anthocyanin's color value for future research. This database will help a researcher and also small-scale farmer to determine the ripeness of the maize. This device is very suitable for a small farmer, new farmer and people that forget the day to harvest the plant, as it will give the real-time notification via an EOT implementation. That's all from us. Thank you.